Hello. In this video I make a little closure about the latest explorations that I did with in relation to the C programming and Python programming. And my purpose here is to translate the C program into a Python program. And one could make a script maybe to make it faster, this process, but it was the first time for me, and I did lots of re-maneuvering of those variables there, and finally I shrunk it down to a representation that maybe is usable. And we observe here this object hash file, and this one is an important file in my C program, but I wish to replicate it in Python. And here we have this Python representation of it. As we see, this C structure is looks like this struct object, or sometimes it's typedef struct, and the structure name is final, and final line here. But here we have the struct declaration this way. And those objects are essentially declarations, or to inform first off the developer how this program looks inside and what it is about. And that's why in C we got all those type names and very precise assumptions about what is going to happen in the program and what the use is. And we see, for instance, here UV type variable that is two-dimensional array, but the array dimensions are unknown. That's why they are pointers. And here we see a three-dimensional array in this line, and this is also two dimensions are unknown, but the first dimension, or the primary dimension, is known, and this is here given as known dimension here in the square brackets. But the rest of the two dimensions are unknown, and they are just pointers. And they are unknown in the moment of the declaration of program initialization, but when the program runs, then they become known, and then they are allocated accordingly. And let's take a look at also where something is allocated in regards of this structured object. And we see here initialization function here, and the initializations comes then with the data. The data is read from object file, is constructed, is prepared for the initialization with many discrete steps, and then the object is allocated, and all those members are also allocated. But not all the subdivided variants are not allocated in the initialization, but afterwards, when the program runs and the user decides to subdivide an object, then those additional allocations are made for subdivided arrays. But the first arrays are allocated here, and they are two-dimensional, and two-dimensional for compact memory access. I remember when I developed this program, then I tried also to eliminate this two-dimensional approach, but the program came up slower. But when we reserve these memories as memory fields, then program is better. Then the memory is compact, memory access are compact. And however, to get an indice or the element from this array, we need to submit two indices for two-dimensional arrays, and they are this element access looks like this here, two-dimensional, and here two calculations are made inside those indices. First of is the integer division, and the second one is modulus operator. And somebody may say it is takes time to acquire one single element from this type of array, but I said that I did attempt to reduce this to one single indice, but this was not efficient. Efficient is this way. And this here is object initialization function, and this is the first initialization, but in these initializations the many members of this object structure are not initialized, they are not touched. Those are subdivided variants, and those subdivided variants become alive later in the program when the subdivision happens. And we see those subdivided variants here. And also there is a lot of OpenGL related arrays here in the object. And those are the buffers, and sort of if I should explain it how it works, then we have those objects and the vertices and the data inside, but when we submit the work to the GPU for the OpenGL, for instance, then we submit those extracted compact arrays that have no so to say unnecessary information in them. They have all the data that is necessary for OpenGL to operate. And a similar way, if I plan to do, for instance, maybe in the future or somebody else plans to do some self-made rendering view, then the principle remains the same. You should just submit into GPU only the necessary data, not the rest of the data, and the rest of these functions then extract the necessary data into those special arrays named buffers, and they are submitted to the GPU with OpenGL commands. But when I navigate here into the Python, then my intention is to make something different, something new, and maybe to implement my own GPU renderer or something like this via CUDA. And this way I declare those arrays here in my Python file. And what about this declaration in Python? Here we see that this is rather difficult to read or understand the Pythonic version of it. And it is also not very precise or correct in the terms of what is intended to say, but Python doesn't give us the means to do those arrays. When I wish to do something, then I could maybe do multidimensional arrays in NumPy, but the NumPy arrays also declare the size, and I have no option to make some pointer type, and or some dimensions are known, other dimensions are unknown. This is not possible in Python, and this way Python is not good programming language in this sense. I cannot really express what I'm intending with those variables and how they look inside the computer. But however, I can intend to declare something that is similar to the C code, but this is not precise, this multiplication here, and multiplication of non-entropy here. But nonetheless, in Python we know that we can change the meaning of variable on the fly, and the Python programming language doesn't complain about it. And let's see how it looks. I can initialize those objects, and they are built up this way that they work, they don't miss anything right now. I can run module here, and I have another file here for demonstrating how in the ideologically how those objects are supposed to work. And we see here this array size. This is the representation of this acquiring a single vertice from the vertice array, and we here see the usage of this array size. And let's take a look what we see, what we get here. I just paste here those commands, enter, and then I create this object. And I say that the object vert count equals the array size. This way we should get only one array, and it doesn't expand to the next array. Then we create this variable here to come up with the equation for the vertice generator. And here this A is used, and then we get this idx variable. This is the index of the vertice, and this is one-dimensional approach, but when the vertice is acquired, then the separate indices are then generated with division and modulus. And we see we acquire the last index, last vertex in the given array, and then we initialize one single vertex inside this object, because we initialized this object already and generated its verts. And then we can test out what are those verts about. Of course, this representation of those vertices is the vertice coordinates here. And I should make this array size smaller for the example. I just restart this shell right now, because it slows down. So I just run it again. we just make this test again with an array size of 10, for instance. Then we get a smaller array size. And we make the same way. And so generating those, getting this indice. This is the last vertex. And now we wish to check what is inside this array. And we press here. What about this representation? This is the, I have this vertex structure translated for Python class, and I added this representation function here, and it returns the vertex coordinates here. And our test is about this setting a single entry in those vertex coordinates. I just make this vertex association here, and maybe I just press simple we see that this has 3 zeros fields. An interesting thing about this Python representation is that those are supposed to be float numbers, but if we declare them as 0.0, then the representation comes also this way. And this is maybe a nice thing about Python. So we just set this one here into another number and print out the verts, and we see here this number is represented here. And about those generators, we wonder if I had used those multiplication array constructors, then it's not the right thing to do. And why this is it doesn't generate individual vertices, but it rather repeats the single instance of the vertex call, and then you get just duplicate instances here inside those vertices. And for instance, when I then change the vertex x value, then everywhere this 9.8 pops up, and this is not what we want. We wish they to be individual instances.